Okay, next is the gas turbine and also combined cycle power plants. So the content of these subtopics are natural gas, gas turbine technology, advanced gas turbine design, the combined cycle power plants, micro turbines, and also environmental impacts of gas turbines. Okay, so first we have to know what is natural gas. So natural gas is a naturally occurring hydrocarbon mixture consisting primarily of methane. Okay, so methane combination with other hydrocarbons, which are the carbon dioxide, nitrogen, and hydrogen sulfide. Okay, so basically natural gas is found in the deep under natural rock formations or associated with other hydrocarbon reservoirs in coal beds. Okay, so you can see here. So basically, it is found in deep under natural gas, natural rock formations. Okay, so same with this figure. Okay, so we can get the natural gas is underneath the surface of the ground. So basically there are two mechanisms on how the natural gas was created. Okay, so first is the biogenic gas, so created by methanogenic organisms in marshes, bogs, landfills, and shallow sediments. Okay, the second one, okay, this one, thermogenic gas. It is created from buried organic material deeper in the earth. Okay. Okay, so natural gas produce lower levels of atmospheric pollution than either coal or oil when it's burned. Okay, so it is also easier to meet emission regulations with a gas-fired power plant compared to the coal power plant. A sustainable energy future must rely on renewable sources of energy, and gas is not renewable. It is a conventional sources. Okay. Most importantly, the supply of gas available in the world is limited. Okay, this is the video on natural gas. I will share with you the video after this lecture. Okay, gas turbine technology. So the turbine is used to give a synchronous generator which provides the electrical power output. Okay, normally the turbine operates at very high rotational speeds of 12,000 revolution per minute RPM or more. Hence, it must be connected to the generator through a high ratio reduction gear, since the generators run at speeds of 1000 and 1200 RPM depending on the AC frequency of the electricity grid. Okay, so it is very important to have a reduction gear. So this is the figure of the simple gas turbine electric power generation. Okay. So we look on to the turbine configurations. Okay. So gas turbine power generators are used in two basic configurations. First one is the simple system. So normally simple system, it consists of the gas turbine driving an electric power generator. So basically, for the simple system, involve three main sections. Okay, the first one is the compressor. Okay, so first one is the compressor. So the compressor which draws air into the engine, pressurizes it and feeds it to the combustion chamber at speeds of hundreds of miles per hour. Okay, and then the second part is the combustion system. It is typically made up of a ring of fuel injectors that inject a steady stream of fuel, okay, this one, fuel, into the combustion chambers where it mixes with the air. The mixture is burned at temperatures of more than 2000 degrees Fahrenheit. The combustion produces a high temperature, high pressure gas stream that enters and expands through the turbine section. Okay, so the third one is the turbine. So the turbine is an intricate array of alternate stationary and rotating aerofoil section blades. As hot combustion gas expands through the turbine, it will spin the rotating blades. The rotating blades perform a dual function. They drive the compressor to draw more pressurized air into the combustion section, and they also spin a generator to produce the electricity. Okay, as I mentioned before about the reduction gear that connects between the gas turbine and also the synchronous generator. So the purpose of this reduction gear is to decrease the high rotational speeds of the turbine, which is approximately around 12,000 RPM, to suit with the generator speeds, which is only about 1,000 and 1,200 RPM, depending on the AC frequency of the electricity grid. Okay. So the next one is the combined cycle system. So this combined cycle system is designed for maximum efficiency, in which the hot exhaust gases from the gas turbine are used to raise steam to power a steam turbine, with both turbines being connected to electricity generators. Okay, this is the figure. Okay, this is a figure of the combined cycle system. So the first one is the simple system, from the field and the gas turbine to the synchronous generator. So for this combined cycle system, the principle is that after completing its cycle in the first engine, this one, okay, this one is the first one, and then the working fluid, so the exhaust, is still hot enough that a second subsequent heat engine can extract energy from the heat in the exhaust. Okay, this one is the first one, this one is the second principle. Okay, usually the heat passes through the heat exchanger. So the heat from the gas turbine will go to the heat exchanger, so that the two engines can use different working fluids. So the first one is use the gas turbine, and the second one from the exhaust gases, it will exchange to steam, and then the steam will be rotating the steam turbine, and then after that we produce electricity from the synchronous generator. Okay, so by generating power from multiple streams of work, the overall efficiency of the system can be increased by 50 to 60%. Okay. Okay, next is the modern gas turbine. So modern gas turbine, the gas turbine combustion chamber is specially designed to produce minimum quantity of nitrogen oxide. The turbine stage of a modern gas turbine comprise 3 to 5 stages of blades. Okay, you can see here it is comprised 3 to 5 stages of blades, operating with an efficiency around 89%. Okay, and then first we have types of gas turbine. The first one is the small gas turbines. So basically the outputs for the small gas turbines is around 35 to 45 megawatt. Okay, and then the energy conversion efficiencies is up to 38%. And then we have the second gas turbine is the larger gas turbines, with the output around 265 megawatt. Okay, so basically these larger gas turbines usually used in base load combined cycle power plants. Okay, slightly lower efficiencies, but for modern large turbines, the efficiency is around 38.7%. So modern development focus on materials that can withstand the high temperatures. Okay, so using single crystal for first stage turbine blades, and ceramics are also being used as an alternative to metal. So the first stage, basically they use the single crystal or the ceramics to withstand the higher temperatures. So intake air must be carefully filtered, filtered to prevent the entry of particles which could damage the blades at the high velocity. Okay, next is the advanced gas turbine design. Okay. So the key to gas turbine operation is the efficiency. Okay, so efficiency is very important. So efficiency both of the compressor and also the turbine. So the more efficient the gas turbine, the more efficient gas turbine, the more electricity it can be produced from a given quantity of fuel. So the higher the efficiency of a fossil fuel power plant, therefore the smaller the quantities of atmospheric pollutants it produces for each unit of electricity. Okay, so this is very important on how the gas turbine was designed in order to keep the efficiency high. Okay, so there are 4 strategies to improve the performance of the gas turbine, which are the reheating, intercooling, mass injection, and recuperation. Okay, but for in this chapter, I will only focus more on the reheating and also the intercooling method. Okay, so for the reheating, so we look at onto the reheating method. Okay, so reheating basically the design would be like this. Okay, so we have here is the low pressure compressor. Okay, so we have inlet here, inlet, and then we'll go to the okay, so we have here. Okay, I draw it first now. I will draw it first, then I will explain after this. Okay, then this one's go to the generator side. Okay, and then here we go to the okay. So we have here is the combustor. Okay, this one we have the combustor, two combustors. Okay, so here you inject the fuel. Same goes to this one. Okay, fuel. Okay, so basically here is okay, so here we have the low pressure compressor, okay, and then goes to the high pressure compressor, the second one. Okay, so if we look at back from the existing system, it's just one combustor system. But for this reheating means that we have two combustors. This is the first combustor. This is the second combustor. Okay, so we add here fuel, okay, to the combustor. So this one we have two types of turbine. Okay, so this one is the high pressure turbine. And then this one is low pressure turbine. And finally, this is the power turbine. And this will be the generator to produce the electricity. So this reheating process involved with this gas turbine split to two separate sections called spools. Okay, so you can see that we have two separate sections. Okay, the first section here and the second section here. So two separate sections. Okay, so a second combustion stage is introduced to reheat the air between the high pressure velocity decrease and the low pressure velocity increase of the turbine. So using this reheating process makes the turbine more efficient. Okay. Okay, regarding the velocity and pressure concept, so it is like a Bernoulli concept. We have here, for example, here, okay, then we have fluid that flows in these sections. So we have here, for example, V1, velocity 1 and pressure 1. Okay, and then we have here velocity 2, pressure 2. Okay, the concept is, okay, the concept is velocity 1 is high, so the pressure 1 is low. Okay, same goes to here lah. So higher pressure velocity will decrease. This one is V2. So V2 low, so the pressure 2 will be increased. Okay, so it means that when the velocity is decreased, the pressure is high. Okay, and when the pressure is low, so the velocity will be high. Okay, it is a Bernoulli concept for this reheating process. Okay, next method for the advanced turbine design is intercooling. So splitting the compressor into two sections, which are a low pressure compressor sections and also a high pressure compressor sections. Okay, you can see in this figure. Okay, this one, okay, as you can see here, this one is the low pressure compressor, and then this one is a high pressure compressor. So intercooling, and we have the intercooler here. So intercooling process, compressing air tends to heat it, and hot air occupies a larger volume. So cooling it reduces the volume so that the compressor actually has less work to do. Okay, so therefore it can increase the efficiency of the system. And then the combined cycle power plants. Okay, so this is the gas turbine based combined cycle, as I mentioned at the previous slide regarding the combined cycle power plants. So the combined cycle is used for power generation and incorporates a gas turbine and steam turbine. Okay, so we have the gas turbine here, and then we also have the steam turbine here. Okay, so gas and also steam. So all of the heat recovered from the exhaust is converted into high pressure, okay, high pressure steam. This steam is used to drive a steam turbine, which converts the energy in the steam to mechanical energy, and then which will be converted into the electrical power. Okay, same goes to this figure lah. The explanation is as before. Okay, so if you can see here, This is the gas turbine combined cycle power plant system schematic. Okay, so the exhaust heat can be captured in a steam boiler. Okay, normally called a heat recovery steam generator here. Okay, so you have here where or HRSG, where it generates steam which is used to drive a steam turbine and create additional electricity. Okay, this one, the first method, which is the gas turbine, and the second method is the steam turbine. Okay, so combined cycle power plants CCPP may employ one or several gas turbine. Okay, so we have this one turbine, second turbine. Okay, each gas turbine is equipped with its own waste heat boiler designed to capture the exhaust heat as efficiently as possible. Okay, so the most efficient plants will employ gas turbines, the heat recovery steam generator HRSG, and steam turbines that have been matched to one another. So incorporated all those things together. Okay. So CCPP can be based on modules of around 300 to 400 megawatt, and the actual output can be increased by adding some additional heat generation within the HRSG, a procedure called supplementary firing. Okay, this one is the explanation. Okay, this is the video that I will share with all of you later on. Okay. And finally is the micro turbine. So there's a new trend in this gas turbine we call as a micro turbines. So it is a small gas turbines which can be used for co-generation. This Z is a combined heat and also power. So with power generating capacities of between 10 kilowatt and 100 kilowatts can be installed in factories, office blocks or small house developments. And this system, the emission performance is generally better than the larger gas turbines. So this is the figure of the micro turbines. Okay. So for the environmental impacts of the gas turbines, so of course it is relatively less pollution compared to the coal-fired power plants, and the most gas turbine power plants burn natural gas, which is just a clean fuel. Okay, compared to coal. Okay, however, they can produce significant quantities of nitrogen oxide, some carbon monoxide, and small amounts of hydrocarbons. So nitrogen oxide is generally considered the most serious problem in gas turbine. Okay, so this is the great switch emission saving for replacing coal with gas. So we can see here, this one is from coal. Okay, this is all the emissions that are produced from the coal power plant, while this is from the natural gas. So we can see we can save emission from after we have replaced the coal with gas. Okay, so by 2020 our aims is 150 million tons of carbon dioxide can be saved, can be reduced after substitute the coal with the gas. Okay, next is the renewable energy sources. So what is renewable energy? Renewable energy, often referred to as clean energy, which comes from natural sources or processes that are constantly replenished. For example, sunlight or wind will keep shining and blowing, even if their availability depends on time and weather. So there are many types of renewable energy sources available, such as solar power, hydropower plant, biomass, and so on. But in this chapter, we will only discuss hydropower plant and also solar power. First, we go to hydropower plant. Okay, so for hydropower plant, consists of, first is the hydropower plant, the choice of site for hydropower plants, constituents or equipment of hydropower plants, small hydropower, and finally the environmental impacts of hydropower. Okay, so we go one by one. First is the hydropower plant. Okay, this is some of the figures of large scale of hydropower plants in Europe. Okay, so you can see there is a very large hydropower plant. Okay, so what is hydropower plant? Okay, hydropower plants harness water's energy and use simple mechanics to convert that energy into the electricity. Okay, you can see from this figure about the hydropower plant. Okay, so hydropower plants are actually based on a rather simple concept. So water will flow in through a dam and then turns the turbine, and also which turn to the generator to produce the electricity. That is the basic concept of hydropower plants. Okay, so it is a generating station which utilize the potential energy of water at a high level, okay, high level for the generation of the electric energy. Okay. Okay, so this is the one of the important equipment for this hydropower plant, which is the hydroelectric dam. Okay, so these plants are generally located in hilly areas where dams can be built conveniently and large water reservoirs can be obtained. Okay, so this is the hydroelectric dam. Okay, so water head is created. So here we have the water head. Okay, so water head is created by constructing a dam across a river or a lake. So this is the river. So we built a dam here. Okay, so from the dam, the water is led to a water turbine. So this is the water turbine. And then the water turbine will capture the energy in the falling water and change the hydraulic energy, which is the product of heat and flow of water, into mechanical energy at the turbine shaft. And then this turbine, okay, turbine drives the generator. So this turbine will drive the generator, which converts the mechanical energy into the electrical energy. Okay. So these hydropower are becoming very popular because the reserves of fuels, which is the coal and oil, are depleting day by day. Okay. So this is the advantages and also disadvantages of the hydropower plant. Okay. So we look at the advantages first. Okay. So the advantages of the hydropower plant are no fuel. Okay, no fuel is required as water is used as a source for generating the electricity. Second, it is quite neat and clean as no smoke or ash is produced. Okay, so it is comparatively simple in construction and also requires less maintenance. However, this is all the disadvantages. First, it involves with high capital costs due to the construction of the dam. Second one is skilled and experienced hands are required to build the plant, and it requires high cost transmission lines as the plant is located in hilly areas which quite away from the consumers. So this is the advantages and also disadvantages for the hydropower plant. Second is the choice of site for hydropower plant. Okay, so this is the main factors in order to choose the site for the hydropower plant. The first one is the availability of the water. Okay, the second one is the storage of the water, And then the third one is the cost and type of land. And fourth one is the transportation facilities. Okay, we look one by one. First is the availability of the water. So such plants should be built at a place, example, river, canal, where adequate water is available. Okay, that is very important. Availability of the water. The second one is the storage of water. Okay, there are wide variations in water supply from a river or canal during the year. This makes it necessary to store water by constructing a dam. Okay, we have to construct a dam in order to ensure the generation of power throughout the year. Okay, the third one is the cost and type of land. The land for the construction of the plant should be available at a reasonable price. And fourth is the transportation facilities. So the site selected for a hydropower plant should be accessible by rail and road so that necessary equipment and machinery could be easily transported. Okay. Okay, next is the constituents or the components of hydropower plants. So there are three main components of hydropower plant. The first one is the hydraulic structures. Second one is the water turbines. And third one is the electrical equipment. Okay. So first is the hydraulic structures. So hydraulic structures in a hydropower plant include the dams, okay, dam, spillways, headworks, surge tank, penstock, and also accessory works. So we look on to one by one. First is the dam, okay. So a dam is a barrier which stores water and creates water heat, okay. So this is what we call as the water head. And this is the dam. Okay. So dams are built of concrete or stone masonry, earth or rock fill. Okay. Next is the spillways. Okay. So spillways, here is the spillways. You can see here, spillways. Okay. During heavy rainfall in the catchment area, the river flow exceeds the storage capacity of the reservoir. So in order to discharge the surplus water from the storage reservoir here, so into the river on the downstream side of the dam, so we need these spillways to discharge the surplus water. Okay, and then headworks. So headworks consists of the diversion structures at the head of the intake. They generally include booms and racks for diverting floating debris, sluices for bypassing debris and sediments, and valve for controlling the water, the flow of water to the turbine. Okay, and then we also have this one is the headworks or the water head, and then we have the surge tank. The surge tank is a small reservoir or tank which is open at the top, in which water level rises or falls to reduce the pressure swings in the conduit. So this is, we have here is the conduit. Okay. So next is the penstock. So this is the penstock. So penstock are open or closed conduits which carry water to the turbines. They are generally made of reinforced concrete or steel. Okay, so this is the figure of the penstocks or conduits. Second is the water turbines. So water turbines are used to convert, the energy of falling water into mechanical energy. Okay, so the principal types of water turbines are, we have impulse turbines and also reaction turbines. Okay, first we look on to the impulse turbines. So such turbines, Okay, this is the figure of the impulse turbine. So such turbines are used for high heats, which is greater than 450 meters. So an impulse turbine, the entire pressure of water is converted into kinetic energy in a nozzle, and the velocity of the water jet drives the wheel, which is the Pelton wheel. Okay. Next is the reaction turbines. So this is the figure of the reaction turbines. So reaction turbines are used for low and medium heats. Okay. So for low and also medium heats, which is below 450 meters. So if let's say greater than 450 meter, we use the impulse turbines. But if low and medium heats, we use the reaction turbines. Okay, so in a reaction turbine, water enters the runner partly with pressure energy and partly with velocity head. So the types of reaction turbines are, we have Francis turbines and also Kaplan turbines. So this is the Francis turbines and this is the Kaplan turbines. So Francis turbines, so it consists of an outer ring of stationary guide blades fixed to the turbine casing and an inner ring of rotating blades forming the runner. So we have here is the outer ring, and then here is the inner ring. Okay, so the guide blades control the flow of water to the turbine, and the water flows radially inwards and changes to a downward direction while passing through the runner. As the water passes over the rotating blades of the runner, both pressure and velocity of water are reduced, and this causes a reaction force which drives the turbine. Okay, so there's a video on the Francis turbine which I will share after this. Okay, next is the Kaplan turbines. So it is used for low heats, okay, and large quantities of water. And it is similar to Francis turbine, except that the runner of the Kaplan turbine receives water axially. Okay, so water flows radially inwards through regulating gates all around the sides, changing direction in the runner to axial flow. So this causes a reaction force which drives the turbine. Okay, so you can see more details on the operation of the Kaplan turbines in this video after this. Okay, and then the third components of hydropower plant is the electrical equipment. So the electrical equipment of a hydropower plant includes the generators. So we have here is the generators, and then we have the transformers, the circuit breakers, and other switching and protective devices. Okay, now we want to calculate what is the electrical energy that generated from the hydro power plant. Okay, so first we have to identify what is the weight of the water available. Okay, W. So W, or the weight, is equivalent to volume of the water times with the density and times with the gravity. So this is the important notes. First, the mass of 1 meter cube of water is 1000 kilogram. So mass is the volume of water. You times with the weight of 1 meter cube of water. Okay. So the gravity is 9.81. So this is the formulation on how to calculate the electrical energy available, which is E equivalent to W times H times with the efficiency, overall efficiency. So where H is the head, okay, H is the head in meter, and new overall is the overall efficiency. Okay. Second is the water flow or discharge Q. So Q is volume of water. you divide by second. Okay, so weight of water available, W, is volume of water times with the density and times with the gravity. So the power produced is P, power produced, equivalent to the weight of the water available times with the heat of the water and the overall efficiency. Okay. So we look at the example of 2.1. A hydropower plant is supplied from a reservoir of capacity 5 times 10 to the power of 6 meter cube at a heat of 200 meters. So find the total energy available in kilowatt hours if the overall efficiency is 75%. So the answer is 2.044 times 10 to the power of 6. Okay, so this is 10 to the power of 6 kilowatt hour. So we look on to the solution. Okay, so first we have to calculate what is the weight of the water available. First is W, weight of water available, is volume of water times with the density. Okay, so you know that the mass of 1 meter cube of water is 1000 kilogram. So we know that it gives the capacity or the density is 5 times 10 to the power 6 of meter cube. So you have to times with 1000. Okay, so and then you get 5 times 10 to the power of 9 kilogram. So this one you have to change to unit of Newton. Okay, then you have to times with the gravity, which is 9.81. So 5 times 10 to the power of 9 times with 9.81 Newton. Okay, and then you will get electrical energy available is the weight of water available times heat of the water and overall efficiency. So the weight is 5 times 10 to the power of 9 times 9.81 times 200 meters and times 75% watt second. Okay. Then you have to change to this one is watt second. Then you have to change to the unit to kilowatt hours. Okay. So one, as we know that, okay, how you get this one is because of this. Okay. So you know that 1000 watt is 1 kilowatt. Okay. So 1 watt is 1 over 1000 kilowatt. Okay. So this one. And then 3600 seconds is equivalent to 1 hour. So we want 1 second equivalent to 1 over 3600 hours. So we substitute here. Okay, that how we get to change from the watt second unit to kilowatt hour. Okay, and then you get 2.044 times 10 to the power of 6. Okay, this one is 10 to the power of 6 kilowatt hour. Okay. Okay, next we continue with example 2.2. Okay, so water for a hydroelectric station is obtained from a reservoir with a heat of 100 meters. Okay, so firstly, you have to know that the heat of water, okay, the heat of water is 100 meters, okay. And then calculate the electrical energy generated per hour per meter cube of water if the hydraulic efficiency is 0.86 and electrical efficiency is 0.92. So we have to, okay, the hydraulic efficiency and also the electrical efficiency. So we have to calculate the overall efficiency of this system, okay. And then we have to calculate what is the electrical energy generated per hour per meter cube of water. So the answer is 775 kilowatt hour. So we look on to the solution, okay. So solution first, we know that the head is 100 meters, okay. And then the discharge, okay, the discharge or the flow rate of the water says that about 1 meter cube per second, okay. And then we have the efficiency of overall. So the overall efficiency is equivalent to we have the hydraulic, okay, hydraulic efficiency you times with the electrical efficiency, okay. Then you can get the overall of the efficiency. So we times 0.86, which is the hydraulic efficiency, and then the electrical efficiency you get 0.79, okay. And then you have to calculate what is the weight of the water available per second, okay. So here we have to use the formulation of weight equivalent to the discharge, okay, the discharge or the flow rate of the water, which is Q, okay. Then you have to times with the density of the water and also the gravity, okay. So for this density, as I mentioned before, mass of 1 meter cube of water, okay, is equivalent to 1000 kilograms, okay. Therefore the density is 1000 kilogram per meter cube, okay. That's why we put it here. So we have here is weight, okay, weight equivalent to 1 meter cube per second, which is the Q, okay, Q, and then you times with the 1000 kilograms per meter cube, which is the density, okay, then you times with the gravity. So from here you can cancel out here, so you got weight equivalent to 1 times 1000 kilogram times gravity. So we can conclude weight per second here equivalent to 1000 kilograms with times with the 9.81, okay. So the weight of water available per second is 9810 Newton. Okay, next we look on the power produced, okay. So power produced is the weight available of the water available times with the height, the heat, and also the efficiency, the overall efficiency. So 9810 times with the 100 meters and times with 0.79 for the overall efficiency, so in watts, okay. Then you can get the power produced is 775 kilowatt. So energy generated per hour. So you have, because we just consider for 1 hour, so the energy generated per hour is 775 times with 1 hour. Then you can get for 1 hour, the energy generated is about 775 kilowatt hours. Okay. So next, this one is a tutorial. So a hydropower plant is supplied from a reservoir of a capacity of 9 times 10 to the power of 8 meter cube at a heat of 250 meters. So you have to calculate the total energy available in kilowatt hour if the overall efficiency is 80%. So this is the solution. Okay, the total energy is 4.905 times 10 to the power of 8 kilowatt hour. So we try to answer this tutorial. Okay. Okay, next is the small hydropower. So a small hydropower is the development of hydroelectric power on a scale serving a small community or industrial plant. Okay, small hydropower can be subdivided into two. First is the mini hydropower, which is less than 1000 kilowatt the capacity, and then the micro hydropower, which is less than 100 kilowatt. Okay, so small hydropower plants may be connected to conventional electrical distribution networks as a source of low-cost renewable energy. Okay, so small hydropower projects can be developed anywhere, but mountainous terrain offers the best potential. Okay, so this is the figure. You can see here the small hydropower will develop at the mountainous terrain. Okay, so this is the example of micro hydropower project from UTHM team at Taman Negara Rompin, Johor. Okay, thus Australia and also Switzerland are both big users of small hydropower in Europe. Okay, so these users prefer to implement the small hydropower because the communities were located in the mountainous terrain often cannot be connected to the national grid. That's why they prefer to use the small hydropower, which is the mini or micro hydropower. So small hydropower plants are conceptually similar to their larger siblings, but the difference is the investment involved. The cost is less, okay, compared to the others, the normal hydropower plants. So normally, these types of power plants have to use the off-shelf turbine, which is the available turbine designs and generators in order to keep the cost down. Okay, and then, but however, the energy efficiency tends to be lower. This is a result from the study by the United Nations Development Programme, UNDP, and World Bank in Ecuador found that about the systems. Okay. So when we talk about the efficiency of this small hydropower, so if under 50 kilowatt, the maximum efficiency is 66% rising to 70%. Okay, for this unit, which is 50 to 500 kilowatt range, and also 74% for the units between 500 kilowatt and 5 megawatt. And then in order to determine the small hydro economic is the important factor is the head height. Okay, so with higher head size, generally cheaper to develop. So for these types of hydropower, the impulse turbine is the best choice, where the head height is above than 30 meters. However, if the head height is less than 2.5, so it is very difficult to exploit. Dam and barrage structures are also similar in small and large projects, but many small schemes use simpler design. Okay. So this is type of the run-off river designs, which is very popular since they involve the minimum of civil works. Okay. Okay, next is the environmental impacts of hydropower. So we have three types of environmental effects of the hydropower project, particularly involve a dam and reservoir, are significant and must be taken into account when a project is under consideration. So which are the inundation, the sedimentation, and also the greenhouse gases. So this is the three environmental impacts of the hydropower project. Okay. So this is the figure. The first one, the figure of the environmental effects, which is the first one is the inundation, banjir lah, you can see here. For example, when there are lots or heavy rain fall happens, right? And then the second one is the sedimentations, okay, because of the development of the dam, okay, it can cause the sedimentation. Okay, first, we look on to the inundation. So after a dam has been constructed and an area of land behind it is inundated to create a storage lake. So it is the loss of this land that normally leads to greatest controversy. And most significant effect of the reservoir, which is we have to displace the people living in the area to be flooded. So a hydropower scheme is usually intended to improve the local standard of living, and that yardstick should be applied to the displaced people. They have to make sure that these people should be better off after displacement than they were before. To achieve this aim involves financial support, which should be built into the project budget. And then it also will affect to the plants and also animal life in the area must also be taken into to the account. Okay, first, unique habitats will need replacing with new habitats in the region of the reservoir, and the effect of fish, particularly migratory fish such as salmon and eels must be studied. So this is the effect to the plants and also the animal. The second is the sedimentation. So another effect of a dam or barrage is to change the sedimentation regime in a river. When a dam is built across a river, the reservoir behind it reduces the flow rate of the water or river, and much sediment can precipitate onto the reservoir floor. So in the worst case, this will lead to the eventual filling of the reservoir with the sediment. Okay? So erosion rates may increase in the riverbed below the dam, and more seriously, important ecostructures which rely on the sediment and its nutrients may become seriously disrupted or even destroyed. And the third impacts is the greenhouse gases. While many of the effects of a hydropower project are negative, the greenhouse emissions should on the face of it be positive. The generation of hydropower does not involve with the creation of the carbon dioxide. Okay, so unfortunately the situation is not that simple, because a reservoir can become the source of the methane. So this gas is an even more efficient greenhouse gas than the carbon dioxide. So a reservoir will become a source of methane. Okay, this reservoir will become source of methane if it contains a great deal of organic material. In the worst case, a hydropower plant can produce more greenhouse emissions than a similarly sized fossil fuel power plant. Okay,